Lang Tran and people like Rob Aitken at the Institute of Occupational Medicine. My background is in occupational exposure assessment, occupational epidemiology, and hence I'll be talking about workplace exposure modeling, and I won't be talking about consumer exposure modeling or human exposure modeling through the environment. I'll be focusing mainly on or only on workplace exposure. In my previous session, I went round the table and asked everyone a little bit to say something about themselves. It took quite a lot of time, and I've got quite a lot of time to go through, quite a lot of slides to go through. So I won't do that. I suspect that you are a varied group of people with various backgrounds, with various stages of your career, and that very few of you have any expertise in occupational exposure assessment. Is that a fair reflection of? I've got quite a lot of stuff to cover, and I've got quite a few slides. I mean, I also have a couple of case studies at the end. I will. Please ask questions if I go too quick. Please stop me if I go too quick. I'd rather have a session that I maybe not go through all of my slides, but we have a good interactive kind of discussion that makes things clearer than that I speak here for an hour and that everything goes over your head. So please stop me when you feel that I'm going too fast or if I don't explain something carefully enough. I like to cover. I'll try to cover these things in my. Sorry. In my presentation in the first hour, and then we will have hopefully a bit of time to work with one of the models that is freely available. I'll start with kind of general occupational exposure assessment for the kind of methods that we have, and especially models for traditional kind of chemicals, so not nano-specific. Then we'll probably move on to kind of nanomaterials and what are specific considerations for nanomaterials that makes them different. So why is modeling from nanomaterials different than for kind of macro particles? Then I'll say a little bit about a control banding tool, and that's our kind of control banding tools are fairly pragmatic tools that allows you to manage risks in the workplace. And I'll explain a little bit about a control banding tool that has been developed for nanomaterials. And that's called Stoffer Manager Nano. I think in your previous kind of an email, I think you've been asked to try to register online with Stoffer Manager Nano. I don't know whether you have web access here. Do you have web access? Yeah. So in the second session, we will kind of use that program to kind of not necessarily model, but do an assessment of potential risk of a nanomaterial in the workplace. And I'll talk a little bit about a kind of other modeling approaches that are not really off the shelf, that are much more kind of research tools at the moment. So that's hopefully what I'll get through today. So this slide kind of gives you an indication of what the reasons are for assessing or measuring occupational exposures. And there's a whole range of reasons why we want to do that, from doing health studies in certain populations to doing a kind of a risk assessment on the reach to my thing doesn't work anymore. To determining compliance, setting controls, etc. So each of those reasons will determine what you want to do or how you're doing your exposure assessment. So if you want to do an assessment for REACH, you probably use a different tool or different assessment than if you want to do exposure assessment for an epidemiological study. Because for REACH, you may want to kind of look at, well, I want to assess what my highest possible exposures are And if they are controlled well enough that there is no risk for the people that are absolutely highest exposed, then I'm fine. However, if you do that for an epi studies, that is not the way to do it. You want to have a much more accurate assessment and precise assessment of a person's exposure. So you will have differences in the way you assess exposure. Today, I will be mainly focusing on what we do for regulatory risk assessment, so on the REACH. Do people know what REACH is? Have people heard of REACH? Who doesn't?
Is it the project?
No. Well, in a sense it is. It's a very big project. And REACH is the European regulations for risk assessment of chemicals. And that requires all manufacturers and importers of chemicals to do a risk assessment of the chemicals under all the conditions. So you need to do a risk assessment for each chemical under each application. They need to show that these materials can be used safely by workers and can be used safely, handled safely by consumers. So it's a huge exercise that has been going on in Europe for the last number of years, and it requires industry to do an enormous amount of work in terms of risk assessment and therefore exposure assessment. And it basically has driven the requirements for exposure modeling in Europe. I have a problem with my I don't know whether the flashing light means that the batteries are okay, it works again. Thanks. Just for definition, I consider exposure in my field of work as the external exposure, and that's basically defined as the contact between the substance and the individual in water, air, or soil. So I'll be mainly talking about inhalation exposure. So in a sense, it's defined as the concentration of the material in air that you breathe in. I'm not considering in my field or in my talk internal exposure, i.e. the dose of the chemical after it's taken up. That's much more. That's covered by other parts of the modeling school today. I think you've probably done the environmental modeling earlier, so you've probably seen a slide similar like this. I imagine that kind of identifies how complex exposure is. We as a general population are exposed to chemicals from a whole array of pathways, from a whole array of sources, and we're exposed through a number of routes, either inhalation, dermal, ingestion, and sometimes injection. And you can see that human exposure modeling of this family here is enormously complex if you want to do it accurately. And it's clear that modeling inherently is a simplification of that complexity. And the simplification that often has, that still is very much present, is that we compartmentalized everything. So we compartmentalized occupational exposure, so people in this environment, and we have treated that separately from consumers' exposure, and we treated it separately from people that are exposed to the environment. And that's basically because it's much simpler to do it that way. Now, clearly, we're not compartmentalized all the time. So I'm exposed because I'm working, I'm exposed because I'm consuming, I'm exposed because I'm part of the, living in the environment. So at some point, all these model tools and all these assessments need to be combined to make sure that overall our risks are controlled properly. And there are kind of like studies going on that try to develop methodologies for aggregating exposure and assessing cumulative exposure, etc. today I won't deal with that. That's yet another complexity. I'm afraid that I'm just going to deal with that small compartment, but important compartment of occupational exposures. Next, I think it's really important to realize that exposure is not constant. It's not a static issue over time, but it varies. It varies minute by minute. If I measure my exposure due to, for example, PM 2.5, it will go up and down depending on what the traffic is outside. If there's a truck going past, it will shoot up, and then if it's a bit quiet, it will reduce. So you see patterns like this. Again, the analogy with traffic will mean that the exposure during peak hours will be much higher than during the night or during the day. So your pattern over time. You'll have differences in exposure during the week, especially in occupations. There are issues that in certain environments you may have start-up processes. You might be cleaning processes at the end of the week. So you have kind of a variability during working days, and you have changes over time in exposures. And sometimes you have these kind of patterns of exposure that there is basically nothing happening, but if you take a sample or you open the process, you get a certain really high peak of exposure. And this is we grapple with this quite, it's quite difficult to take that into account, all that variability. And most models often don't take into account variability at all. And I think that's because a lot of the time we don't really know how to explain that variability. We call it random variability because clearly it needs to have an explanation somehow, but we don't know what that is. And it's even so that in the workplace, if you put two people together doing exactly the same task, you will often see that these exposures of the two people are completely different. Either because one is short and one is tall, maybe one is left-handed, maybe one is right-handed, maybe one is much more careful in the way they kind of deal with the products that they're handling than another person. And it's very difficult to predict that. So that leads to the concepts of variability in exposure and uncertainty. And I'm sure that you come across those terms before. And variability and uncertainty is different, although variability may lead to uncertainty. But variability is something that is real. We can't really improve on variability. Variability is something that is existing because of the natural processes. My exposure isn't constant, but will vary over time and over years, etc.
But you can study only right-handed people, for example.
Yeah, but you can so you can narrow your focus, yes. But that means that you're changing the scope of your work. So by changing the scope of your work, you might be able to. So I can say I'm only studying exposure on a Friday afternoon for right-handed people who are over 1.80 meters, who work very carefully and where the RPE,
I mean, that's making it a little bit.
Yeah, but even then, yeah. So you.
I'm sure it's tough to reduce variability by focusing on certain.
Yeah, so you can reduce it. So you can change the scope of your work, but you don't change the variability. You're only saying, well, I'm not studying a number of people that are in my tail. So you're basically limiting your scope. But you're not reducing your variability. I think you're just basically reducing the scope of your study. Yeah. Uncertainty, obviously, on the other hand, you can kind of like work with. You can kind of improve by using better methods, better tools, by increasing the number of measurements that you take over a certain of a certain population. You can reduce your uncertainty in assessment. Okay, when we and especially in the occupational exposure assessment, we often have, we use measurement a lot more, I think, than in, for example, consumer exposure assessment. We have a tradition in an occupational hygienist that we measure a lot. And that's basically because it's relatively easy to measure in the workplace because you got people there working at a certain place. And it's easy organizationally to put samplers on them for a certain period of time. So we have we have done a lot of measurements, and based upon those measurements, we have developed kind of statistical models that looks at, you know, what's the effect of certain tasks and how that task kind of how is that a determinant of the exposure. So you can develop kind of statistical models. We also developed kind of mechanistic or deterministic models that basically tries to explain and describe how an agent goes from the source through the environment to your receptor, and try to kind of describe that. And we'll show you a little bit of a model that we've developed in a bit. And then, you know, Bayesian models, as you're sure are aware, are becoming more and more in vogue. And the advantage, obviously, of that is that you're basically using a kind of, you can use, you know, mechanistic models with empirical data to come up with a more precise or accurate estimate of your exposure. A lot of people in occupational exposure assessment often say, you know, should we model or should we measure? My viewpoint personally is that you can't measure without having a model, even if that's implicit. So even if you take 10 measurements in this environment here that we have in this room, you get a distribution. Now, quite often we say the data is log normally distributed, which means that it has a tail to the right. In my view, that's a model, because by applying and assuming it follows a log normal distribution, we can describe that data, and we can then kind of identify what the probability is that exposure is above from a certain level. So modeling or measuring, I think you're always model to a certain extent. And clearly, the advantage of Bayesian models is that you explicitly combine you can combine kind of your prior knowledge about exposure with empirical data. I won't give you any examples of Bayesian tools at the moment, although I'll show you one of the models that we've developed in one of my projects. It's really useful to develop conceptual models, your conceptual idea about how exposure occurs. And I think that's relevant for any kind of situation, whether you model consumer exposure, whether you model environmental exposure, or whatever, or, you know, any kind of certain more narrow population. I think you have to develop some kind of conceptual, and it can be really simple, like the ones I'm going to show you. But it allows you, and it helps you in kind of interpret your results and understand why results are different, and it also helps you develop kind of exposure models. And these are really not very difficult. These are, for example, this is a fairly simplified conceptual model for inhalation, and it's basically kind of understanding what processes are occurring when exposure goes from the source to inhalation exposure at the receptor. And basically what happens is that the source emits either a kind of a chemical either into the air or to a surface. If it's on the surface, you can have some kind of exchange by re-emission into the air. And the air can become air in the breathing zone. Either, there might be some kind of barriers in there that local control or something like that would reduce the amount that goes to the breathing zone. But basically, there are a number of processes that allows you to kind of estimate how much goes into the breathing zone, and then that's inhaled. What I mean by the breathing zone is basically the air around your head. I think within occupational exposure, we define it as within 30 centimeters of your nose or something like that. So that's basically a kind of fairly simplified conceptual model for inhalation exposure that can and has been used to develop mechanistic models. Similar you can do for ingestion exposure. Clearly, there are some different pathways that go from the source to ingestion, and this is ingestion exposure, again in the workplace. It's inadvertent ingestion exposure because people touch their face when they're working, or put a pen in their mouth, and these surfaces may be contaminated with agents, either because it's emitted in the air and then is deposited on surfaces that you then either kind of put in your mouth directly, or these surfaces might contaminate your skin or your clothes, and they are in contact with your mouth. Or these sources can actually perhaps even directly contaminate your skin and then go into ingestion. And then you have a similar one which looks fairly similar to ingestion for skin exposure. So for dermal exposure, that has either causes an uptake of the chemical through the skin and thereby lead to systemic dose, or it could be an exposure that's not taken up by the skin but has a local effect, for example, an irritant. And again, the pathways are fairly similar then for ingestion exposure. The only thing it stops here at skin. So these kind of conceptual models will allow us to start developing mechanistic models that kind of explains how the exposure goes from source to pathways. And we just need to kind of define parameters that explains these arrows. And again, it's very complicated to do, but with a number of simplifications and by calibrating numbers with real data, we can come quite a great deal. So those are the conceptual models. These conceptual models have been used in developing exposure models, and at various levels. And I said a little bit earlier about REACH, and REACH is a huge kind of process that's happening at the moment, and where industry are required really to do a lot of work, and because it's such a lot of work, it's impossible to do all of that at a similar level of accuracy and precision. So within the REACH process, we have what's called a tiered approach. It means that the first kind of assessment that you do to see what the risks are for a certain chemical or certain agent in a certain scenario is to apply a kind of simple first-tier screening models that allow you to estimate, get a conservative estimate of exposure. What I mean with conservative is that it's an overestimate. The uncertainty is upwards. So I know that my exposure is not accurately assessed, but it's assessed at a very high level. So most of the people will be below that, or all of the people below that. And if your risk assessment shows that there isn't that exposures are controlled sufficiently, that's okay. You're finished. You can deal with that. Now, if that first tier assessment shows that there may be still a risk, then you can either do two things. You can either go back to your scenario and say, right, rather than having a kind of open process, I'm closing it, or I'm putting a better ventilation system in place, and then do your first tier assessment. Or you can say, right now, I think I need to do my exposure assessment more accurately, and you can either do that by using more complex models, or by actually going into the workplace and take a lot of measurements to see what the exposures actually are. And so that's a kind of tiered approach that's happening under REACH. And this is again a kind of the same thing really, but shows that basically tier 1 models are kind of fairly simple but not very precise, and the more you kind of like get towards either higher tier or very specific approaches, you kind of increase your precision, but you also increase your complexity and the cost, obviously, that's associated with that assessment. And as you can imagine, chemical industry are probably quite interested in trying to reduce the cost as much as possible. We've kind of like developed a tool with a number of other people called the Advanced REACH tool, and that was basically mainly led from people at TNO, but also with us and HSL. This is not in your handouts, by the way, sorry. I've put these slides in later. That allows you to do a higher tier exposure assessment using a Bayesian approach. And so this model contains a kind of a mechanistic model that kind of describes in quite some detail the conditions that are applied in your environment, and that predicts an initial exposure, and then it allows you either to kind of like use your own data, your own measurements, or select data from a database to do to run a Bayesian model that provides an update, an even more accurate exposure assessment. And that model is available freely from this website here, and can be used by for a wide range of chemicals and a wide range of applications. It can't be used for nano, I have to say that, but it can use it can be used for powders, but not on a nanoscale. The way it kind of works is that we have our source here, and we have our kind of receptor, and basically there's an emission from basically this follows this conceptual model again. We have an emission, we have some kind of control measure or not that's at the source that reduces the emission. We may have an enclosure or of some sort around that emission, and then we have the substance kind of dispersing through the air in the environment. There might be deposition to other surfaces and re-emission. There might be, there's ventilation going on, either either natural or mechanical ventilation. There might be other sources in the workplace. There might be the worker might be working in an enclosed environment, like maybe in a control room, and he may have he may wear some kind of some personal protective equipment that will reduce his exposure. And within that model, we've identified these modifying factors that will allow us to model that whole process. And these are, we kind of identified 9 of them, and within these 9 modifying factors, we have identified a number of exposure determinants. The first one is intrinsic emission potential. Now, what do you think we mean with that? Has anyone got an idea? What would be the intrinsic emission potential of a liquid be if you're working with a kind of a liquid product? Yeah, exactly. The volatility of the volatility plus the actual concentration of the material. And for what about a powder? What would be the say it again?
Suspension from movement.
Yeah. Yeah. We have a kind of an empirical measure that's called dustiness, which is basically very difficult to predict. But the number of kind of test setups have been developed. That's basically, throwing powders into a tin or in a rotating tube, and that just measures how much dust comes off that powder on a certain controlled condition, and we call that dustiness. So the higher the dustiness, the more emission. And so so those are the 2 main ones for intrinsic emission. What about activity emission potential? What do you think would mean with that? What would determine? What are determinants of your activity that will lead to higher or lower exposure levels?
What you do with the material? So
Yeah.
if you use it in some way.
Say that again?
How you transport it, how you store it,
Yeah.
how you treat it.
Yeah. We kind of identified it as a number of things, like quantity, because obviously quantity is important. If I do an activity with a few grams compared to a few tons, that has different there's a different scale there. So if you're handling a few tons, the potential of exposure might be much higher than if I'm handling only a few grams of material. It's the energy. So if I carefully scoop a few grams from one place to another with a very low kind of falling of the powders, it's much less than if I drop powders over a few meters into a kind of a container. And it's a containment. How, is it an enclosed or is it an open? So a number of factors allow us to try to develop specific determinants under the activity emissions. So we have gone through all of these determinants, local control, separation, segregation, surface contamination, and based upon the evidence of the literature, we've identified what these determinants are and then scale these, kind of put relative scales to those determinants. So for local controls, we looked at whether it's a booth, whether it's a kind of fume cupboard, whether it's a kind of extraction hood, and based upon the evidence of the literature, we applied kind of like relative scores for that. And these relative scores are kind of basically used in a couple of simple equations to calculate at this point still a kind of a relative score of exposure. And these are basically we've combined, we basically assumed a two compartment model. And the first compartment is the compartment that's called a near field. And that's my basically a box of 1 by 1 by 1 or something like that around me. So that's my near field. So if I have a source that's in my near field, it will almost lead directly to exposure. And so it will lead to much higher exposure than if a source is in the far field, for example, at the back of this room. But that far field exposure source might still lead to an exposure for me. So we modeled them separately. And these are the equations of those kind of like what the contribution is from near field sources and the contribution from far field sources. And within these factors, we have identified determinants of exposures and we have quantified those. So we have scores for each of those depending upon the description of the activity and the description of the substance. Yeah? Sorry, respiratory protective equipment. So that's your mask that you have, and that's why it's applied at the end. So you have your emission, you have your activity, you have your local control, you have kind of personal behavior, and you have surface contamination, and so we have and there's a kind of dilution because of ventilation. And again, that's kind of modeled for the near field and far field. They are slightly different, and they're combined.
Is the stuff in the brackets just percentages, so just dimensionless?
Yeah, at this point, they're dimensionless. They're dimensionless kind of factors, and they could be, they range from 0.001 to, they could range, so it's not a percentage. They're actually a relative score that could range depending upon the factor. Now, within art, within other kind of models, they've stayed with this. They kind of stayed with, for example, Stoffer Manager that we will look at later on. They'll apply similar equations, but they have stopped here. Now, what we've done is actually compared these relative modeled predictions with a large exposure database, and that allowed us to calibrate these relative scores into actually concentrations. So when we apply this model in art, it will actually translate it into concentrations. So we will get milligram per meter cube of a certain chemical by basically calibrating this relative score with a very large exposure database. So that's, I think, probably in occupational exposure assessment. At least for generic tools, that's probably the state of the art where we are. I mean, there are kind of other tools available that allow you to model exposure for very specific applications. But for generic application for a generic model, this is probably the state of the art. Sorry, the pun. But it doesn't allow you to measure or to model nano exposures. And why is it not possible to model for nano? For example, art. Why can't we use that for nanomaterials?
You don't have the database that you just mentioned.
Yeah. So you don't basically have the data to calibrate it. What else? What are the other problems with nanomaterials? These are a bit, yeah. Why would that be?
The wall effect for much
Yeah.
larger, so the things are different.
Yeah.
To those for
Yeah. So you have basically the size of your particles will make sure that they behave differently, and they're not constant. You know, if I emit a source here with a certain size distribution, and it's not just that source kind of like transported, well, that contamination transported cells from A to B, and it changes, yeah, because you have processes like coagulation and agglomeration. The distribution will change from A to B, depending upon particle size distribution, depending upon the concentration. And the other issues and that will then affect the level of deposition, the level of diffusion. So those are kind of like complicated issues that these other models haven't taken into account. And lastly but not least, we have this ongoing discussion about what metrics are important for nanomaterials. And we still haven't really figured that out, what to measure, what to model. So all these models that I've showed earlier are modeling, or that art model that I showed, they are modeling mass, and only mass. And for nano, we don't really know what we want, right?
Is there a database for powders or dispersions like that? Not nano, but
Yeah.
just common industrial stuff.
Yeah. We can for dispersion of what you mean in air for transport. No. I'm not entirely sure, but for powders, we can look at what the dispersion is. We can model that, and we can basically model the dilution, but not necessarily that. If you try to take into account what the process, how these particles interact with one another at high concentrations, we have to kind of like apply different kind of different kind of equations that are possible but are not yet in these models that I showed earlier.
Is there a database for powders?
I don't think there's a data. Well, there's probably. I don't know what you mean with that. You see,
Well,
there is what you mean database for powders of concentrations in air, or database of powders of what, of the granulometry, or
no, that's just one entry to the equation. So if you work with a powder, it can similar to a molecular material you're talking about, can propagate in different ways.
yeah. But we have very little empirical evidence about, first of all, about how much. What the dust, because we're quite pragmatic in this area. If there's very little data about how, if I do this with a nanoparticle, if I put it into a beaker, how much comes off, and it's very difficult to model that. You need to kind of empirically measure that, and we can model things about how at certain concentrations, and I will show you an equation later on that allows you to do that. How the distribution changes because of coagulation, etc. But there isn't really any databases of concentrations in air.
It sounds good. So it should be, to get it right, it should be a part of that reach framework. So if I have a titanium, for example, and then that if I assume that if it's a powder state, you say dustiness enters somewhere.
Yeah.
So that just
Yeah.
put some number to the dustiness.
Yeah, but there is not really a database available for that. You have to probably kind of either guess it or empirically measure it, and basically it's a bit of a nightmare because it should really be fairly simple. It should really be kind of like directly related to the fineness of the powder, but there's a lot of other things that are involved in that. So we don't really understand that enough to be able to model that particular dustiness. So we either have to guess it or we have to kind of measure it. Sorry.
Just one question. So art is limited to pollutants which are static in a way, so they can transfer during transport.
Yeah. So it basically is for
It's
aeros.
also for organic chemicals that might transfer during transport or absorb in particles or something.
Yeah, it's basically we've kind of calibrated it for vapors and for power and for dust.
For coarse powder.
Yeah, for coarse powders.
Will you maybe give us the limit of, or the size limit of what you consider microscopic dust as it was previously recognized, and what is now this unknown area of nanoparticles?
Well, I think there is I think issues with coagulation you probably need to start taking into account when you're dealing with particles that basically are defined as nanoparticles, so 100 nanometers or less. I think that's where I think there are some kind of criteria where you kind of, but I think that's
criteria of concentration also.
Yeah, it's also clearly, but above that you probably don't really need to take that into account that much. Yeah. There's limitations. We don't really think because obviously there are other processes in macro. And vapors and mist, for example, there's condensations and evaporation going on, which we haven't modeled in art either, and that we could kind of try to look at that at some point. But as always, it's a simplification of reality models, and that's something that you always have to keep in mind. I'll go through this very very quickly. Because I'm sure that you're are aware of that, and that probably people kind of like are more aware of that than I am. But nanoproperties can be described in a number of ways to deal with surfaces, to deal with composition, to deal with distribution and size distribution, shape, concentration, and any kind of like metric. So it's they're quite complex. It's not as simple as our traditional chemical exposure, which we can collect on a filter on a tube, we give it to our lab, and they come with a number. This is the mass. It's much more complicated than that, at least for the time being. There are also different forms, and I think we quite often this distinction that's quite often made, and the main distinction is between kind of tubes or fiber-shaped materials and spherical materials. But there are other kind of materials and other shapes that are around too. And that is the issue of metric. What metrics are we most interested in? And depending on the metric, your size distribution will differ. So if I measure it by number, it's clearly much more determined by your smaller particles, and if I'm interested in mass, the larger particles will dominate. And that will have it's important for us. Are we interested in mass or interested in number, both in measurement and in modeling? So this will shows you a little bit what will happen with nanoparticles of a certain size and a certain background. So this is this is a kind of a source of original of a nanoparticle, and this is distribution of a background. And if that's emitted in air, a number of things will happen: dilution, diffusion, coagulation, deposition. That will make this distribution shape change. And especially if there's at certain sufficiently high concentrations, and also when there's a background, and when the difference in the size between the background and the nanoparticles is large, there will be things like scavenging going on, and that you can see that the distribution of your material of your aerosol will change, and that's kind of like complicated things to kind of model in there. There are some things done at the moment, but they're still not available as a tool. I mean, there are kind of research kind of equations, numerical equations that we can use, but there's nothing available that as practitioners we can use. So this is again summarizes why nanoscale may differ from macro scale. Properties change with size. You have diffusion becomes more important. At low levels, gravitational forces may become negligible, and you may have kind of electromagnetic forces that are important, which we don't really know how to deal with that at the moment either. So what do we do for modeling for nanomaterials? Now again, we can apply a kind of a tiered approach, and there are a number of examples that have been developed in kind of defining what this tiered approach should be. I think there's a German kind of like publication from a number of people who have described a tiered approach, and it mainly at the moment is using it's very similar. It's using initially a kind of like an easy, simple kind of tools to screen out areas where you think that exposures might not lead to a risk, and then kind of concentrate on areas where you need more information on the exposure. And for the first tier, you might be able to use things like control banding tools, and I will show you the Stoffer manager Nano in a bit. For higher tiered exposure assessment, at the moment, unfortunately, it's pretty much measurement that we can use, and measurement using quite complex specialist equipment. So there's a lot of need for an advancement in this higher tiered exposure assessment for nanomaterials. So control banding tools as a first tier. Are people familiar with the term control banding? Have you heard this before? No? They're basically very pragmatic tools that are used by practitioners to basically because of the lack of knowledge and the lack of really information, allows you to make some kind of decisions about the level of control you need to implement in your workplace. So there's a number of control banding tools that basically say, well, how is it a fiber, is it a powder, yes or no? How much? What's the quantity of the material? And is it and what's the hazard of the material? And basically characterize these kind of like things with 3 or 4 questions, and basically rank them into high risk to low risk, high exposure to low exposure. And if it's high, they say, well, you need to really do something about controlling your exposure by enclosing it, by giving very, very kind of high protective RPE, levels of protection, etc. And if it's low, you basically say, right, you're probably okay with just general housekeeping, etc., etc. So that's what control banding tools are. So very simple models that are, some more or less based upon knowledge of exposure, but sometimes not, and will allow you to make some kind of decision. It's a tool to make some decision. It's a tool for practitioners. They're not research tools. They're not let you obtain a very accurate estimate of exposure or an accurate estimate of risk. So the number but these tools are necessary, but because we're not there yet we don't really have the more refined tools to do the more proper risk assessment. So a number of organizations have developed these control banding tools, and here is a number of these listed. So in Switzerland we have something called TMAS. In the US there's something called I keep calling it nanocarbon black, but it's nano control banding tool. And TNO, they have developed the Stoffer Manager Nano, which is available online. And in Denmark, they have developed a model called NanoSafer, which is available online. It's mainly in Danish, I think. And then there's an ANSYS Nano developed in France, which I don't think is available online. So there's a number of tools that you use to as to determine the level of control required.
So
Yeah.
just a small question. So these are tools that can be enforced for, like there are some products that are already in the market for research. So the companies would use those tools to say for the MSGS data sheet, you should wear a mask, you should wear gloves.
Yeah. That's what I mean. That's and not for research, but for the nanomaterials that are actually being produced, and used downstream. So, yeah, that would be the you're at the minimum you expect people to kind of gone through these control banding tools. I say at the minimum because there's a lot of uncertainty around them, and they're not, because there's no data available. We don't really know. We kind of think they're kind of conservative, and we think about that they are kind of conservative, but we don't really know. We haven't really evaluated these tools to such an extent that we have a high level of confidence. So this is the minimum what you would do at the first tier. So this is, to see how simple these tools are. This is the kind of level of information that's required for the exposure. And for Stoffer Manager Nano, they require the most detailed information about the source domain, so what kind of activities is it, the product appearance, dustiness, the moisture content of the powder, what the task is, task duration, frequency, if it's in the near field or the far field, the volume of the room, the ventilation, if there's any kind of separation of the worker from the process, PPE, if it's clean and if it's maintained. That basically is all the information that's required to come up with an estimate of exposure. So it's very limited, and that's by the most extensive. I mean, if you look at this one, it's basically the dustiness, the amount, the frequency, and the duration, and something about control. That's the information that's available or that's necessary to run that model. And NanoSafer is a little bit in between Stoffer Manager and the others. So they're kind of simple, really simple tools. So I don't know what time it is. I will show you a little bit about Stoffer Manager Nano and how it works. And then a little bit about a kind of numerical equations that allows you to do a bit more advanced stuff. And then we'll use Stoffer Manager Nano to go through a number of case studies. Sorry, yeah. Of course.
The maximum workplace concentrations usually mass-based.
Yes.
Is there also something going on in more to particle number concentration?
These tools, they don't actually give you a concentration.
No, that's true, but I think if we model this and handle this, we need to know what we are focused for.
Yeah.
And I think the particle number concentration is an important factor.
Yeah.
I just wonder if this is taken into account already.
They're not taken into account here. They basically, you see, it's a relative score. It's a relative score of exposure, and it's probably a mass-based score rather than a number score. But it's not specified, and so this is a kind of a unitless kind of ranking of exposure.
Well, that in particular, but NanoSafer has a lot of units in it, so.
NanoSafer, the background of the model has a kind of a module that allows you to kind of estimate things like coagulation and stuff like that. So it will, but they don't give you that. It doesn't actually give you that. And I'll jump straight away to there are kind of numerical kind of equations that you can implement in a kind of mathematical software that allows you to basically model the change in your number concentration by in different bins, so in different kind of size, basically depending upon the distribution at your source, and a function of your homogeneous coagulation. So that means the coagulation from the particles from the source. So if I emit a certain particle with a distribution, they will kind of like react, well, not react, they will coagulate with one another. And there's heterogeneous coagulation. So that's the coagulation, the scavenging from your nanoparticles with the background material. So you can implement this, and if you're a mathematical modeler, this is not complicated. But again, there are a number of simplifying things that you need to take into account. Also, here you have a function of gravitational settling, diffusion losses, and dilution losses. So if you know, the problem again obviously is you need to know this. You need to know your distribution at your source. And how do you know that? At the moment, there's nothing really that allows us to predict that. So we have to kind of go in and measure that at the source. But if you measure, this model will allow you, if you implement it, to measure your distribution of your emission and kind of model what a worker would inhale depending upon where his position is and depending upon ventilation and room size, etc. So this will allow you to kind of model the distribution over time. And we're at the moment at the IOM trying to implement this as well, that it allows you to kind of model this over space, so that you also kind of have this as a near field and far field model. But we're kind of working on that at the moment and trying to see if you can fit it with some experimental data. So if you have a model in house, they should be able to implement this relatively easily.
So where do you include the structure of the agglomerates into your model? Because you say down in your slide, you talk about the structure of the agglomerates, the fractal or spherical.
Yeah, I think they're kind of like somewhere. There will be. I think they're part of your K. So they will have kind of like basically correction factors for the fact that you don't have spherical agglomerates. So you've.
Also in the gravitational setting, the diffusion, because they change the coefficients of the shape, because of the shape of the particle.
Yeah, yeah.
Where do you find the information about the coefficients, the convolution coefficients?
Well, it's yeah.
For you. Yes.
But yeah, it's I think you can. I think that there is data available or models available that allows you to kind of estimate the this is, I think this is from a paper by Snyder, which basically kind of graphed. This is a bit of a complex kind of graph. This is the size distribution or the medium radius of your source, and this is your background, and this is your correlation rate. So you can see that basically the bigger the difference between your size of your particle of your nanoparticle with the background particle, the bigger your correlation rate is. So there are kind of like, I think this is, I don't know whether this is based upon modeled or empirical information. I think there are some kind of models that allows you to estimate that.
Statistical output for all sizes.
Say that again, sorry, I don't understand that.
You can calculate it assuming all possible sizes, all possible.
Yeah, yeah. Well, exactly, and this, basically this model takes into account the whole array of distribution. So basically, it kind of like it integrates across all your sizes with this function. So if you have a numerical modeler and you have somebody who understands a little bit about aerosol sciences, you can implement this model, and I think it's quite useful, and we're doing that at the moment to link between exposure and dose. Because I think that's where it's important. That's where it becomes important to know how, what you inhale, and you can link that then to your kind of dose metrics. But it clearly is a different level of what we talked about, control banding, because this is much more, much more complex than the simple tools that we talked about before. I think I was at Stoffer Manager, which, going back to the simpler tools, this is a kind of a freely available tool developed by TNO that allows you to do allows you to kind of control or try to implement relevant control measures in your workplace. It provides a simple score of hazard, exposure, and risk, and then allows you to basically decide what is appropriate control measures. There's a few kind of criteria that you need to kind of consider when it's applicable or not. So particles should not be soluble. It's for engineered nanoparticles. The particle size is smaller than 100 nanometers. All specific surfaces is greater than 60 square meter per gram. If it's higher than that, you basically kind of use your the traditional tools. If it's not if your primary particles is already kind of greater than 100 nanometers, i.e. it's not a nanomaterial, right? You can use either Stoffer Manager or ART or whatever. But it includes so basically it does include some kind of underlying mechanism that takes into account agglomerates and aggregates.
What is it different if it is synthetic or natural? Why the second criterion is there?
Yeah, well, I think it's. I think I don't think there should be a difference. There would be a difference in the whole modeling. I think it's just they just kind of said, well, these are it is designed for engineered nanoparticles, not for particles that are. Sorry?
Combustion.
Yeah, exactly. It has a similar kind of source to receptor kind of conceptual model as what I showed with ART before, but it's a little bit simpler. But it takes into account near field and far field. It takes into account how the substances are handled. It takes into account things like local and general ventilation and personal enclosure and PPE. And these are the equations that are used for calculating a relative score of exposure. These are not absolute score, but relative scores. And it's basically a function of the concentration due to near field sources, far field sources, and ds is background concentration. And it has a function. It kind of basically applies functions for control measures, for GF is for general ventilations, and TF is kind of for duration and frequency. And basically what they've done, you don't have to give the scores yourselves for these. They have developed a document, again, kind of like made some either educated guesses or scores based upon evidence that basically they've already linked. So what you have to do in the model is basically say, right, there is local exhaust ventilation. The room is 100 to 1,000 cubic meters. This is the type of activity. This is the dustiness, etc. So the model has already, the tool in a sense has already kind of like assigned the scores for those kind of determinants. So you only have to kind of include the determinants, so the factors in there. So that's a kind of a relatively simple tool that you can use, that's freely available online, that allows you to estimate exposure in a unitless relative way. And in fact, the tool online doesn't give you the relative score. It just basically it gives you an exposure group, either 1, 2, 3, or 4, or something like that. if you, I mean, but it's relatively, it would be relatively simple for you to kind of like just implement the equation yourself using the scores that they provide in the report that is published. How are we doing with time? Oh. Does anyone know the time?
20 minutes.
Sorry?
20 minutes, 25 minutes.
We have 20 minutes to for session 1 or session 2?
Session 2.
Session 2, okay. Well, that's all right. So, for higher tier assessment for nanomaterials, briefly, we have measurement techniques for nano, because that's pretty much what we have at the moment. We have measurement instrument. Unfortunately, these are some examples. I think most of them are from TSI and measure number, surface area, or the size distribution. Most of them, unfortunately, are still a large, expensive, complicated equipment. There's some projects going on, there's developments happening as we speak. And there's a meeting today and tomorrow about a nano device project that aims at developing cheaper tools that allows you to measure exposure to nanomaterials in the workplace. But they are still kind of like a little bit away from being kind of like commercially available. So I think if you only have 20 minutes, then I suggest that I basically finish this session and that we then go to some kind of case studies that you have in your handouts that we can use to get an estimate of risk using the Stoffer Manager tool. So I'll kind of first summarize, I think, where we are with nanomaterials and exposure modeling in general. I think exposure assessment is really determined why you want to do it. So whether you're on first tier or second tier, whether you're doing it for regulatory risk assessment or epidemiology or other reasons. We have fairly good tools for exposure assessment for chemicals and macroparticles, but we are currently lacking really good validated tools for nanomaterials. We have some control banding tools that are available for pragmatic applications for practitioners, again, but they haven't really been validated or calibrated very well. There are instruments, both measuring and modeling, that are under development, and hopefully within the relatively near future, we should be able to perhaps kind of update the art model so that we also have a nano art tool that will give us a little bit more confidence about the exposure assessment that we're doing. So that's my first kind of talk. Do you have any questions so far on this part? Have you all registered for Stoffer Manager? Do you have access to the internet here? So what I suggest we do in the remainder of the 20 minutes is to look at that. And we have I've in the handouts you have a number of case studies, and I suggest we just go over just maybe one or two of the case studies, and basically see how the Stoffer Manager Nano works. So this is case study 1. Which is basically a bagging of a powder. Sorry? Yes.
Do you want us to be logged in?
If you could, yes.
We have to choose a room. It's about...
It's inhalation.
What's that?
Or you can do it in English.
Well, this is in Dutch.
Yeah, but there's a tab that makes it into English. And make sure that you're on the nano module.
Control banding? That's what you want us to choose, control banding. Or quantitative exposure or reach exposure?
It's reach.
Reach.
But it's well, you have to tap the nano module. So make sure that there's a tap on the nano module that you tick. Oh. So you need to kind of make sure that you're in here on the nano module, and I think you have to kind of be on there when you log in, because I think if you're in there and then you log in and then you switch to the nano module, it kicks you out for some reason. I don't know what is this computer linked to the internet too?
Should be.
You have wireless access, so
Okay.
I assume that it should work.
Sorry?
Oh, it's connected.
I think so. I hope so. We can, if I have wireless access here, we can do the first case study kind of like in a communal way, but I'm not sure how. Okay, that works. No, why? It's much more exciting. And I must say that I, although I'm Dutch, and obviously I am thereby biased, I have not worked for or being employed by TNO. So I'm not choosing the TNO tools because I have a vested interest. It's I don't. No. That's always the. Oh. Yeah, I don't even know my own email address anymore. Okay, so I go to when in logged in. You go to I think it's no. Okay. You can go to a new risk assessment, and then you kind of come to this front screen. So let's call it just bagging of FE. The source domain. So that's basically what type of activity it is. So what should we based upon the case study report, what should we include here? Is it release of primary particles during actual synthesis, handling of bulk? I think it's handling of bulk, aggregate or agglomerate nanoparticles, right? So you pick that, and then you go to step 2, open step 2. I think I've done this before, so it fills in the thing already. So it's a powder, because that's by definition. I haven't really picked the supplier or the PIS or MSDS number. That's because I don't really have that. So first of all, what you need to do is identify your dustiness. And I can either put in here unknown, because the case study doesn't really give me that information. So I would either put in unknown, or I put in very high, because if I don't know it, I might kind of assume what the worst case is. But let's put unknown because we don't know it. Then the same thing is with the moisture content. I don't really know the moisture content, so I've assumed, or I assume it's low, so less than 5%. I don't know why I've called it frais, but let's just keep it that way. So the next thing is, do you know the exact concentration of your nanocomponent in your product? You can either say yes, and then you have to kind of like put in the concentration, either 100%, or you say no, and it gives you a kind of some kind of band. So let's say it's a pure product.
What is the unit of that concentration?
Yeah, it's a good question. Yes, it's mass. It doesn't actually say, but
it's 100, it doesn't matter.
Yeah, exactly. Yeah. Well, to be honest, I think I think they haven't specified that, because it's such a crude model that they probably assume it's not. It's not, because the differences are really between whether it's anywhere there or whether it's something along these. But you're right. If you look at it,
Number and mass,
yeah, no, I agree. Then it doesn't matter. Pure is pure. Isn't it? So does the product contain fibers or fiber-like particles? I said no, because I assumed it's spherical. And then from the on the next slide, there is information from the there's some kind of hazard information from an MSDS sheet, which says that it's kind of irritant, but also it has some tumorigenic effects have been observed, and the registry of toxic effects of chemicals contains tumorigenic and or carcinogenic and or neoplastic data for components. So I don't know. It suggests there may be something more than, well, it's definitely kind of, it's definitely not non-hazardous. It's either kind of like irritating, because that's what it suggests, or it may be even mutagenic or carcinogenic. Any toxicologist amongst us? What would? Yeah. We'll stick with carcinogenic then. Yeah. That obviously that doesn't have an impact on your exposure modeling, but it does impact on your risk control banding assessment. So the next step is it asks you to characterize your task, and this is it already becomes quite not kind of unambiguous what we're dealing with here. So bagging of powders, how would we kind of describe that? Is that handling of products with low speed or little force in a medium quantities, or is handling of low speed or little force which lead to some dispersion of dust? I have no idea. It's definitely, what we can definitely say, it's not products with high pressure or speed. It's not relatively high speed or force, unless it's dropped from a really big height. And then you might say, well, there's a lot of, but if it's not dropped from a big height, it's probably not that. So it's either that. We don't really have information. It's not handled in an enclosed container, so it's not that one. So it's either the bottom one or that one, I think. Any preferences? This one? Or, yeah? Or the bottom one? The worst. Well, the worst obviously would be something like this. But it's not. I don't think we will get high pressure. Sorry? Yeah. Do we? Yeah. Yeah. Well, we can. We can. We can.
High pressure. Handling this material should involve high pressures.
It's bagging of powders. I don't think it's necessarily very high pressures or speeds. It's no.
So it's either the one for the last medium. This
one? Okay. So you can see already there's a bit of it's not necessarily unambiguous. It's how you interpret things, and I might interpret things different from what other people do. So let's stick with that one. Then I think we have information about the duration of the task. Is that 2 to 4 hours? If I remember correctly, or 4 to 8. Yeah. And the frequency is about 4 to 5 days a week, I think. And then the next question is the task being carried out in a breathing zone? So is it a near field source or far field? Well, we say it's yeah. And then is there more than one employee carrying out the same task simultaneously? Does it say anything? Only one person. So the next thing is the work area, and it asks questions about the room being cleaned daily. I think it says yes. Is that right? And it's inspected. I mean, the one thing that you can do, obviously, you can go back and say, right, what if it's not cleaned? And what if what is it not inspected? I'd be very surprised if it makes a huge amount of difference, but it probably does. Volume, I think, is defined as that. And I think they say there is mechanical and or natural ventilation present. And then we go to step 5, which is the local control measures. Does it say local exhaust ventilation, I think, isn't it? And the work that's already completed because it's in the breathing zone. It doesn't matter whether the worker is in a cabin or not. And then RPE, was it RPE? No? So we select none. So these others here, they're basically, you see that as, it gives you kind of different factors. And that will mean that they have different types of protection factors. So clearly a hood or a helmet with supplied air system will have a much higher be much more protective than a filter mask, which is one of these masks that you see people walking around with if they're kind of handling powders or doing some sanding or so. So it's none. And then you get the risk assessment. And it will now kind of calculate with these kind of equations that I showed you earlier. It will calculate the score. And that score is kind of translated in a time-weighted exposure class. And that goes from 1 to 4. It's a shame that you can't actually see what the score is. But it would be, like I said, with the report and the equations, it would be relatively easy to go through that and calculate that. But it's a relative score, so you would get 97 or 65 or 323. But what that means, it doesn't mean anything. But what they've done is they kind of translated that in a time-weighted exposure class, and that goes, I think, from 1 to 4, with 1 being low exposed and 4 being high exposed. And similarly, they have a hazard class, and I think from memory it's either 4 or 5 classes, and because we said it's a carcinogen, it's the highest hazard class. So that gives it a total weighted risk score of 1, which means I think it's the highest score, or the most risky score. So you need to implement more stringent controls, either by RPE or by containing it or whatever. So you can then...
Can you get to the classification of those values from here?
From the risk score?
Yeah.
Yeah, I think if I close this. So basically here it says scoring of the risk. So basically it doesn't actually say what one.
It has
does it?
The table right there at the bottom.
Okay. Yeah, thank you.
Yeah.
So these are the kind of. In fact, D wasn't really the highest hazard class. It was there's another one above that. But exposure class is from 1 to 4, and then the risk is from 1 to 3. And then clearly, when you have a high risk score, you will, and I think probably within this tool, it will also kind of direct you to what kind of control measures you should implement. Yeah. So it's a tool for practitioners. It's not a tool for exposure scientists. And if you want to kind of like understand more about what happens in exposure, and how that exposure is relevant for those, you will either need to go out and measure, take much more measurement, or get some kind of somebody to implement a numerical model. But even then, you need to have good, accurate information as your source information to be able to allow to run that model. So, really and truly, for occupational exposures, modeling is still plays second fiddle really to measuring. I think would be my kind of summary of it all. There are a number of other case studies that you could go through it at your leisure, and I'm happy to ask or answer questions that you may have online, online at a later stage, or about this or about other kind of aspects of what I talked about today. So I think we're probably due for lunch and some fresh air. So I'll probably, if there's no questions anymore, I suggest that we leave it at that. I hope this was useful and at least near what you had hoped from this session. I think it's quite different, the different sessions, I imagine. The PBPK modeling will be much different from this. And again, this probably will be different from the environmental exposure modeling. And I think it's because we are at different stages, and we are of development of these various areas. Yeah? So I'll leave it at that. Hopefully it was useful, and I thank you for your attention.